All right, testing. So today's goal is to probably we'll do regression. It probably take 2 weeks or sorry, 2.5 class or so to finish this regression. So probably we would like to talk about what's regression, but you would probably know this from what we mentioned ANOVA, right? ANOVA is comparing means of different group and to see if different group have different means, right? Assuming they have same variance and assumes normal distribution. And here we extend this idea to say more than 2 groups, or even allow continuous grouping in the or allow even at the ordinal, right? So in the ANOVA, grouping are nominal, right? So the groups or locations which have no particular order information. So there's group A and group B, right? We'll talk about our school. We have different college and see whether different college have different GPA or different income, right? Or different study hours. And these are different college. Usually you don't usually can't put really ordinal data, right? Or numerical number there, right? Because basically just like one college is one college, so you cannot say too much. But for regression, we are trying to exploit the ordinal or order data on the grouping, you know? So in say the grouping is age group, right? Age would be young and old, right? And in the ANOVA, we didn't use it, right? We didn't talk about how old you are can be used as the way to explain your income. But now regression allow us to take this numerical measurement to try to give us a hint or the model to explain or to predict what happened to your income, right? So that is the idea, is we want to say study how education and income, right? ANOVA, you can do it, right? Say suppose you can take it into income of people with different education levels, right? Those people who have high school, those people who have undergraduate degree or master degrees, right? So you can talk about, right? And ANOVA, right? One of the maybe it's the thing about this, right? Your ANOVA, you can talk about income, right? And you have say income of high school, right? And you can also compare income of undergraduate, and you can also compare income of a say master, Ph.D, right? So that, or doctoral, right? So you have 3 different group income. You can see if they're different or not, right? And you use ANOVA. Basically, you do not use the information that people do undergraduate have more year in school compared to high school, and people study master and PhD have several years education more than undergraduate, right? So if you can use these ideas, then that comes with regression, right? In the other words, probably what you will see, the data you have is like the following, right? So probably you have a bunch of data here. Oh, what is the x-axis? Maybe this is education measured by year, right? This is income, right? And then you probably have some people who study the this is coming from, right? This is a bunch of high school, right? And then you have what's the color I use? Okay, the bunch of people actually coming from, I don't know, it's coming from this undergraduate, right? And again, you have another bunch of people who actually, okay, here, 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 here. And these are the people who just the masters, right? Master PhD, right? So you can see that the group mean is different, right? Say the master and PhD have higher mean, right? Say mu of master and PhD, right? And this would be the mean of, say, undergraduate, right? And this is the mean of high school, right? So you can see the mean are different, right? But you do not tell us how they're different, okay? And maybe in this diagram, you can easily see that we can come up with what we call a linear model, right? Maybe this is the line that would be the best able to describe how education are with the income. So this is an extension of the framework from ANOVA, because now we know different group actually would have, you can use one measurement to describe the grouping, and that help us to give us a equation. Maybe I use another color, maybe better, right? So how to draw a line, the best fit line is what we call a regression, or we have a linear regression, right? We draw a linear line. So that is the main idea of this topic, is to basically draw a line in a scatter plot, right? And you have to notice how this line, can be compared. It's an extension of the idea that we do ANOVA, right? ANOVA is just talking about different grouping of different mean, but we didn't exploit the fact that sometimes the data, the grouping, do have more information, okay? And then we exploit it. Is that clear what we're doing? Is that okay? So is that clear why we want to study linear regression? Is that clear? Any question before we proceed? Is that okay? So that is coming from how you, from ANOVA up to the linear regression, right? It's basically just like using more the group information it contains. So I hope it becomes clear why we study ANOVA first and then we study regression, because it's further generalized, right? Because remember, ANOVA actually generalized the t-test, right? Two sample t-test. And here, regression is generalization of ANOVA. So it's getting increasingly more sophisticated. Okay. And in the other than income education, so what would be the business application? Would be advertising or sales, right? So you try to see if the company doing more advertising, is it going to improve sales? Usually yes, but how much more, right? The question here is that ANOVA probably you can do is showing that company having more advertising lead to more sales. But the problem probably is how much, right? Because if you want to study what is cost and benefit of advertising, we need to see if I spend $1 more on advertising, how much more dollar of sales I would get to justify the spending. So that is the key part of this, why we want to align, because we have a how to describe a precise, a linear, relationship, that how they're related, and you can make a decision, right? Because ANOVA just tell you they're different. Okay, you spend more advertising, okay, you have more sales. But how much more? ANOVA didn't give you this idea, how much more. They just tell you, okay, you spend more, you do advertising on FIFA World Cup, okay, you have more sales, but how much more? Does it justify the cost we spend on hiring a advertising agency to do so much money and do so many work, or is it worth it? And similarly, another application, right, you probably see these days is about drug dose and recovery time, right, because the COVID, right, the pandemic. So the problem of here is, okay, we have more drugs, right? Or you can imagine this is just like how many number or sort of vaccine you want to get, right? The problem is whether you have one more vaccine or two more vaccine. Is it going to improve the reduce the pandemic transmission, right? And you have the cost and benefit, right? Then how can you know what is the optimal? Then you need to come up with a model. ANOVA can only tell you the direction, but don't tell you exactly the magnitude. So regression is trying to give you the magnitude. So that is the key. Is that clear? So maybe I add the word here, right? So the key here is the magnitude. Okay, it's the. So here is like the key thing is ANOVA. Okay, only tell you they're different or not. Okay, so just direction. Okay, regression actually tell you the magnitude. Okay, exactly how these things are, if you're able to change one dimension, how the other dimension varies. Okay, so I hope it become clear how they are different. And so here that is the data we have. Okay, regression is going to be a huge topic. We can only have 1 or 2 weeks left. We're only able to give you a scratch of the surface of what it can be done. And our class is 2011, and you can imagine that the next class 2021, the whole class, the whole course of that, the second semester one, the advanced class, is basically studying regression. Okay, you can imagine the whole course is devoted to regression. So you can imagine that is a huge topic. So we just only, as I said, just scratch a little bit surface. And we're only doing our job on only 2 variables, X and Y. Okay. And if you more than that, I mean, that would be something that left it to the other class. Okay. So if you remember the data we have in the ANOVA is X1, G1, and so on and so forth, right? Xn, Gn, okay? And G1, Gn is grouping, right? The grouping I just maybe a nominal, usually the nominal data, right? But now we don't have the nominal data. Now we have another called Y, is a numerical data, okay? Instead of nominal, so this is all our numerical data, okay? Numerical. And so here we have slight changes in notation. Okay, the grouping is like the G. Okay, but now our grouping used to call X. Okay, and the variable that we're interested in is called Y. Okay, so there's a slight changes. Okay, so we are basically want to see our interest is Y, but the grouping is by X. Okay, but the group is a continuous. Okay, so you may ask why we do this kind of change notation. I don't know. This is what all the textbooks is using. So I can't really go against the world and go against your textbook. And just to remind yourself, X is now the grouping, okay? And Y is something we're interested in, okay? No particular reason why they do it this way, but that is the standard. So as we have said, we're trying to look at the line that best fit all their points, right? And you can imagine that why I want to do a line, right? You can do a curve, right? Potentially look at the graph here, right? You can easily think that a curve may be a better fit rather than line. And the reason why we want to focus on a line, because line easier first. Second is we're doing introductory thing, so we just focus on the simple one. So focus on a line. So that's why we have what we call a linear regression, because we're on a line. Okay, and it is possible. Actually, you might have learned if you go to further class, in the next course, the advanced class that they'll call the you can fit a contraste, you can nonlinear, so it can be nonlinear regression. Nonlinear can be done, but it is not the concern of our class. Okay, so to fit the line, we use this form, but this is, if you learn high school, probably you will learn more familiar form as y to the mx plus c, but this is just c is just an y-intercept, right? Same as here. Okay, b the slope, right? So b is the slope. Okay, and a is just the y-intercept here. And probably some of you ask why I don't use this famous formation y mx plus c. This is because in the regression, people do a plus b. Okay, so that's not something I invented. So I just follow the standard notation you see in the book. Okay, and so the notation we have is simple linear regression. Simple means we only use one variable. Okay, and if you want to have a more than one thing, right? So y can be say y1 can be say x1, z1, right? Can be two grouping, right? Two-way ANOVA, right? In that case, it would be more complicated. Okay, but our concern is just use one variable. Okay, and we're doing a line. Okay, so that is the thing. Basically, what we learn in this class is simply a scatter plot. We find a line to fit the points in the scatter plot. So that is what we are focusing on. And as I want to emphasize, this is the tools that how to find the best fit model is the thing that most of the statistical analysis is based on, right? Because basically you go to data and try to find a model that is going to explain the data well, right? You even look at, say, how people do artificial intelligence, big machine learning, big data. They're all somewhat variation of this kind of regression or some kind of modeling. But regression will still be one of the most useful thing, right? If you ever try to go to very advanced data analytic class. Okay, so we just work on something very simple in this class. Okay, is there any question about the scope of our study? Okay, this is with the scope is we limit to this one. Okay, if there's no further questions, and I will continue. This is the graph, right? So this is the data. What we do is trying to see how x and y are related, and in this framework, you see they are positively related to each other, right? And well, we want to find a line, okay, to best fit it. And the first question is we want to find the best line, okay? So what doing the best, right? We need to come up with some criteria to define what's the best, right? If every point can fall on the line perfectly, then it's easy to see this is the best line, right? But in data, no matter what you're going to draw a line, you can't fit the line best, okay? So there's some departure to from point to line, right? Regardless of how you measure it. So how can you define the departure from a point to a line, okay? Potentially, in this framework, at least you have 3 different obvious criteria to define what is the departure from a line. First one, is probably the most straightforward one that you learn if you motivated from mathematics point of view. Is what we call the perpendicular distance, right? You can imagine that I would look at the distance perpendicular to here, and how long is this guy, okay? And this is the one of most natural one, right? And in this one, basically, you're looking at the distance perpendicularly, right? So you are not biased towards x or y, right? If you swap x and y, then this distance would be the same, no matter how you use it. It's symmetric, okay? So it's a nice one. And from mathematical point of view, this is also the way you measure the distance, right? I mean, when you learn high school, okay? So the way you measure the perpendicular distance is indeed one of the way that you can do the measurement, as indeed one of what we call the, I think this is called Lyso regression. Okay, but this is not the concept today. We're not talking about this. Okay. This is commonly used when you look at machine learning and big data and analytics. Okay, but today the concept not this one. Okay, I'll explain why this is not good. Okay, and the other one is the other two is looking at the vertical distance. Okay, and the third one you can imagine is the horizontal distance. Okay, and the one we pick will be the vertical distance. Okay, and you may ask why I pick this guy. Okay, instead of the two other guy. Okay, the reason, if you recall, what we're doing is we are trying to use to see whether different x lead to different y, right? X is our what we call the sometimes we call the explanatory variable. When you try to explain, maybe use the other term. Use the other one. We'll call independent variable. Okay. Y is called dependent. And sometimes they call this is explained variable. And this is what we call explanatory. I think it's spelled like this one. Explanatory, maybe right. Explanatory variable. So this is one explain the other one. Okay. And and I mean this group X is grouping, right? So how well the model behaves is look at I have this particular X, right? And this is my model, right? So how well is it doing, right? Is the whole vertical distance, right? Because this is how well the model perform. So that is why we look at the vertical distance. It's because of we try to see, use X to predict Y, right? Or to explain Y. So the reason is X is our thing, is our information. Y is something the output, right? X is, you can, if you don't want this terminology, X is just the input, right? And Y is the output, okay? And this is the model output, okay? And of course, your model output, right? Of course, you measure how good is your model by comparing how the output perform compared to what supposed to be, right? So that's why we look at the horizontal, vertical one, right? And the horizontal one is a ill fit to fit the purpose, right? Of course, it has some meaning, but it's not something we're looking at, right? Of course, blue and also the purple one also do the job in some sense, but this is not the primary concern, right? Because we are using X to predict or explain Y. Okay, so I hope, because for example, remember the introductory example we have, the working example we have is this is the education, right? This is income, right? So that's why we were trying to look at the education, how it lead to our income, and it is meaningless to compare different income because they're different group, right? You compare this and this is not meaningful. But you compare given the same education, how your model behave is something we are looking at. Is that clear what we are doing? Is that okay? Okay. So I hope this become clear. So here is the mathematical statement that we have just said. Okay. So this is data we have. Okay. This line we have drawn. Okay. And the vertical distance. Okay. And the way we define is how your data different from your model. We take the data minus your model. You can do the other way around, but this is the way we follow. Doesn't really matter anyway. So we looking at how to minimize the d, right? So we look at the distance. So basically, is what we do is maybe here, right? So what we're trying to do is look at the distance, right? So this is, so the point is this is x, this is y, okay? And we have a bunch of data here, okay? And the best fit line is like this, suppose, okay? And we evaluate based on this distance, right? And suppose this is D1, this is D2, this is D3, D4, D5, D6, okay? So the question is being that you want to make this is all distance smallest, right? So one of the criteria you can imagine will be, because actually these are positive, right? Because you take this is, say this is x1, y1, right? This point, and this point will be x1, y1 hat, right? Remember what's y1 hat? Y1 hat is coming from a plus bx1, and what's a and b, right? For this line, right? This intercept is a, right? The slope is b, right? So you have this line, okay? And one of the criteria that you can find the best fit line is to minimize some of the absolute distance, right? You can consider the case where you have absolute distance of d1 plus d2 and so on and so forth. Okay, you want to minimize this, okay? And minimization is try to find a and b, right? And this would be try to find intercept and slope, okay? Just keep moving the line so that the distance, some of the absolute distance are minimum, okay? And actually, you can do that. I think this is what we call the median regression. And the idea we don't use this is like the variance, okay? We don't want to use the absolute one because it's difficult. So that's why what actually we do is to minimize this instead. D1 square, D2 square, okay, up to Dn square, okay. And here that's why this name is called least square. Okay, this is called least square method. The reason is being that least square method is because finding the least square, and because remember this is positive, right? This is negative. First, that's why you need to use the absolute value, right? But absolute value is difficult to handle, so that's why we do an we do the square, okay? And just to remind you, the calculus, if you do square, allow us to handle this minimization problem very easily, okay? And if you use absolute value, the calculus is not very nice. Probably you can't really figure out what is the minimum. And that's why historically the classical method, which is still widely in use, is what we call the least square method, which we are using. Okay, we're trying to find a line that minimizes the sum of vertical square distance. Okay, so that is called the least square method. Okay, this method fitting this line has a very long history, even before the statistics come about, right? So this is invented possibly by a famous mathematician called Gauss, okay, one of the greatest mathematicians in the history of mankind. So he used this to actually, if some of you study physics and you know, he get famous because he used this formula to predict actually the return of Hamill comets. Okay, at that time people are just predicting where the heavenly body moving, and he got famous by having a very precise prediction. And before the computer comes, he able to do it very nicely because he used regression. But anyway, so the question is, we try to find the slope and intercept to minimize this sum of square distance, right? Which is what we have here, right? Sum of square distance. And how do we find this? This is a quadratic objective function. We try to have a multivariable, two-variable minimization problem. And actually, we have a closed form solution. But I guess, as I said, in this class, we don't require calculus, okay? So if you want to know the detail, you can check out the slides, how to prove it. That's not difficult. I think the slides, the proof is somewhere in the background. You can look at that if you want to know how to prove it. But it requires some multivariate calculus, which is the first year calculus in the math department. And I guess not many of you have studied it. So I just present you the main result. And the main result, I think, is very intuitive. So even though we have to take it as given, but I try to convince you that this result is pretty straightforward. Okay, so I don't tell you how we get A and B. If you want to look at the slide, the technical one, we focus on telling you what this formula is. Okay, so here we tell you how do you get minimize the square distance. Has two equations here. The first equation here tells you, okay, if you try to rewrite this one, okay, we write in a maybe more friendlier way to see is y bar is equal to a plus bx bar. So what does this mean here? It means that your your line will go through the center of your data. Okay, so what do you mean by center of data? Okay, so here I have a data set here. Okay, and I forget about the y dimension. I just calculate what's the average of x. Okay, then I would have look at the data, probably is here, which is give me the x bar, right? Which is called the average of x. Okay, here I ignore all the information on y, just calculate the average of x. I can do the same for the y dimension. I forget all the information on x and I calculate the average of y. That would allow us to, again, similarly calculate a y bar here. Okay, this is the y bar. Okay, and here this what we call is the center of data, right? Because this is exactly the center, right? Which is x bar y bar. So our first regression result tells you if we want to minimize the sum of square distance, the line must pass through the center of data, which I think is very intuitive. You try to minimize the distance, right? So going through the center would be a good idea, right? If you go elsewhere, you move the center, you should also reduce it. Is that clear, the first statement? Okay, the first property. Of course, why this is correct, you have to prove it, but without proving, we show you this is very reasonable way of seeing it, okay? The second one, okay? The second one, okay? The second is something that probably you would not be surprised, okay? So here B actually has a two-part, a fraction. The numerator part, okay? So that must make it easier, okay? To how to you observe this is to divide both numerator denominator by n, okay? If you divide both, actually that would make the equation, the formula the same. But when you divide by n, or if you like n minus 1, doesn't really matter. If you like n minus 1, it's the same thing. Okay, if you do the same, doesn't really matter. What you will get from here, if you try to recall what is the numerator. Numerator is simply the covariance, right? And the denominator is simply the variance. Okay. And which probably is not very surprising to see. First, remember the equation is the line is like this, right? A plus bx, b the slope. Okay. It should not surprise you. The line should be proportional to covariance, right? Because covariance said the following, right? How x and y are related, right? If covariance is 0, there's no relation, right? So your predict line will be a flat line, right? If the covariance is positive, they are above the mean at the same time, below the mean same time, right? Because this is what we mean by covariance, right? Whether they are in this region, right? I mean, I try another one in order to avoid too congest, right? So this is the idea of covariance. If you still recall x and y, right? A bunch of data here again, okay? And I have a line here, okay? And I have I have y bar x bar, right? Remember what is covariance? It's positive means that, right? It's positive means it's likely to be here and here in the blue region, right? More likely to the other region, then we'll call covariance of x and y will be positive, right? So that is what we have learned, right? And right, because it's when x is covariance positive means when x is above the mean, y is also likely above the mean, right? The more positive it is, the more likely that it's more likely to fall in the blue region rather than outside the blue region, right? That's what the covariance means, right? So exactly you will see the more likely that fall into this region that it will be have positive, right? So that's why the slope, right, should be proportional to covariance. Is that clear? The reason is being covariance exactly describing this, right? If say covariance is 0, that means that actually the line you should fit is actually y bar, right? In the case of covariance is 0, right? That actually means B is 0, right? That basically in that case A will be y bar, right? And indeed y bar is the best predictor, right? Because you try to use x to explain y, but turn out x and y are unrelated, right? It's covariance 0. That your model should be just a line. a horizontal line, right? So that's why your line is proportional to the covariance. Is that okay? Is that clear why this case? Now, let me explain the last item, which is the denominator before we break, okay? So the denominator is the variance, right? So we know the numerator, right, divided by n, or n minus 1. This is the covariance, okay? And this is the variance, okay? And I divide the variance by x, okay? So why do we have divided by variance of x, okay? The idea is actually very simple. It's inversely proportional to b, okay? The idea is the following, okay? If you have y equal to a plus bx, okay? And if you simply change x measurement, okay, say from centimeter to, I don't know, millimeter, okay, means x is multiplied by 10 times, right? You should expect the regression to give you the same thing, same prediction, except the b should be 1/10 of the original one, right? Because the same thing, just change the scale of x, right? So b, if you x the measurement change in this, b should be just changed from original value, say b from 10 over divided by 10, right? So the new b value just will be reduced by 10 times, right? So although I didn't talk about this, actually can prove if b here, right, this formula, okay, if this multiplied by 10 times, okay, this covariance will be increased by 10 times, okay? This is math, I'm not going to show you. But the variance, if you remember, if variance by 10 times, if by 10 times, the variance will be by 100 times, right? The reason is like this. Remember the formula, variance a of x is a squared variance x. So put a is 10, okay? So 10 over 100 is 1 over 10, okay? So this is exactly why we need to rescale by variance. It's because of our regression is independent how you measure your x. If you make x 10 times bigger, your b will be 10 times smaller, right? Because a and b, the same thing, right? So it doesn't really matter how you measure x, okay? Is that okay? Of course, you can see if I change the y by 10 times, say, and b will be again changed by 10 times, right? Because of the formula you have. The a and b, the b will be bigger by 10 times. And a as well, okay? So this is a kind of, I don't know, little bit mathy. So let me go to the graphic, explain, and then we'll break, okay? So very quickly. So first is, I have said already, you will pass through the center of data is here, okay? X bar, Y bar. I'm not going to, because this graph we discussed, so we just skip this one, go to the other one. As I said, if you have positive covariance, the slope will be positive, right? So this is very natural because it must pass through the center of data. The line must be there. So what it is, okay? And if covariance 0, right, then the best fit line will be horizontal line, okay? And similarly, if the covariance negative, because it passed through the center, right, it means b is less than 0, right? Because you can't fit a positive one, right? Because negative means most of the points are actually in these two regions. So that's the best fit line you should have, right? And here I have the graph with the variance increase, right, by variance increase, look at the graph, is you should see in this way, is the data originally is red, okay? You just increase the variance with respect to x, which means that I keep the y the same, right? I make the x little bit further away from the x bar, right? Because that means by x bar, the variance of x increase, right? Just everything moving a little bit away, okay? With respect to x bar, right? Okay, x bar, you just stretch the x variable a little bit longer, right? Actually, when you stretch them, right? Of course, the slope would reduce, right? Because you stretch them, the fit line will just flip, right? And you can imagine that if you keep stretching and stretching, the variance increase to so large, B will become 0, right? Because you keep stretching, you just hit until it become a horizontal line, right? Actually, that's what we expect to be. Okay. So I think the last point, so I have 2 more points. Okay. So if you, as we just said, right? If you double the x, you will halve the b. That explains why there's a fraction. I think I explained already. It's just the cm to mm story there. Okay. And here, I don't know. Should I update this one? I don't know. I think I should have updated the slide. But anyway, here if you increase y by 1, okay, every data go by 1. Okay. And it means that your intercept will also go by 1. Okay. Because there's a formula mean, right? Because the formula says the following, right? A equal to y bar minus bx bar, right? And go by 1, actually don't change the b, right? And no change the x, and change y by 1, so a go by 1, right? Because there's no change in these two, okay? And this go by 1 because every y go by 1, the y bar go by 1, right? So that is the y of this, okay? And these graphs are nothing but trying to explain that these two formula, okay? If you don't like the graphics, these two formula will already have everything there, okay? So these are those graphics just trying to make sure that you would have a deeper understanding on the graph. But if your math is good, then there's nothing more than simply going to this one. Okay, so I think we should break. Another break, what we talk about is here, this is just a mathematical model, right? There's nothing about probability, right? Nothing about data. Okay, this is the bigger data, but nothing about probability, right? So we will talk about probability after the break. Okay, we'll talk about an important idea, what we call the Gauss Markov theorem. Why we are trying to predict using this formula here. What's the good thing about A and B? We will show you A and B will be a good estimator, okay? If the data generate between x and y actually linear. We'll give you a model trying to say these two are an estimator. You assume the data generation process follow a bell curve, okay? So we talk about this after the break, so don't worry. We'll try to see why A and B are good, okay? And let's a break of 10 minutes, okay? I go around to see if you have any questions. So I hope it becomes clear that to you how you can do this least square method. Okay, so maybe I quickly go about how you can calculate this. Okay, so we have data. We have 5 data points. Of this is the data point, and the way I write is x and y, but sometimes you can write x and y, depends on what data you have, but depends on the structure. So, but usually people present this way, right? Yx rather than the other way around. Okay. So this data. So the question is, how can you estimate the slope intercept? Okay. I'm not going into detail, but I try to illustrate the idea how we can do it. Okay. So here we start from scratch. Okay. Here data. I can calculate the average of x and average of y, right? And here I have x and y, and how I come up with this. The third column, right, is basically coming from 1 minus 3 is -2, 2 minus 3 is -1, so on and so forth for the third column. The fourth column is similarly 4 minus 6. Okay, maybe I use the this color, right? 4 minus 6. Okay, it's given 2, -2. And if you multiply these two columns, you get 4, -1, 0, -6. Okay, because this time this gives you this guy. Okay, some of you say there's many calculations, but I create this from Excel. Okay, because this is how I create. That's why I draw this table, right? So that's why you don't need to worry. This is usually done by use Excel, right? And you by now is able to create this from Excel quickly, right? Copy and paste. And if you square the third column, right, you get the last column, right, raised to the power 2, right? -2 times negative is 4, right? So the sum of the fourth column, okay, you add up everything there, right, give you 7, right? The sum of xy, okay, sxy. And if you sum up all this column, give you 10, okay? And by construction, it is automatically give you the slope of B. Let me use other color, okay? B, which is 0.7, and A will be just y bar minus B, right? Which is 3.9. Okay, so I think would be useful to show you how to do Excel, because this is too many calculations to be done by hand anyway. Okay, and I will show you the shortcut how to do it. Okay, so let me start the Excel first, and let's do it quickly. Okay, and how can we do that? Okay, let me quickly type the data in. This is y, this is x. I have 4, 7, 6, 4, 9. I have 1, 2, 3, 4, 5. Okay, so oh, sorry, this is not the first column. Okay, it's here. I put data. Okay, So what we're going to need is the following, right? So remember the equation we have is here. A is equal to y bar minus bx bar, and B is equal to covariance xy over variance x. Okay, so that would be the two equations that we are using. Okay, so from the first equation, you see I need x bar y bar, which is mean of x and mean of y. So it's x bar y bar. Okay, and that is easy. X bar simply average, right? Average of x. Okay. In case this Excel dies, I just save it at desktop first. Okay, so we can also do the average of y. So don't worry, you will be asking to do this question again in your assignment. Okay, but you can use Excel to do it. Okay, so there's no need to use your calculator, I hope. But if you are welcome to use calculator, because for those who are accounting, they were happy to do calculator anyway. So covariance xy and variance of x. Okay, covariance xy. Either you can use, you may ask whether you use the population or the sample one, they're the same thing, as long as you do consistently. So let's use the sample one. I think that would be better because we're handling with the sample. Covariance doesn't really matter, use x or y. So x or y first, so x or y. Okay, column A and column B. Okay, that gives you the covariance. Okay, and variance, I will use sample version of variance x. Okay, so that already gives us all the information, right? Because how to find A and B? Okay, first find B first. The slope will be just covariance over variance. Okay, so that is the main thing, right? Covariance over variance. Okay, and A is just the y bar minus B times x bar. Okay, so that's come with this one. So this is, if you ask to run a regression, you just need, I don't know, 8 lines, right? If you have ever to calculate, right? And of course, you probably would ask, okay, is there any smarter way to do it? Yes. Excel is pretty smart. You have what we call the slope function, or what we call intercept function. Okay. And it immediately gives you the result. Okay, let's do it. Slope, we just slope. Okay, just type slope. And then you put all the y first and x second. Y first and x second. Okay, so that gives you the answer here. Oh, okay. And you can do the same for the intercept. Intercept all the y and all the x. Okay, and this Excel slide is at the back of your set of slides. I covered earlier because some of you actually worry about calculations. So I cover here first, so that make sure that you don't feel too worried about handling this manual calculation. Okay, I mean, I intend to cover at the end of all our theory, but I put it here because some of you expressed concern over computational heavy calculator process. But I hope this convinces you. This is I'll upload this file to the Blackboard at the end of the class. But I hope this convinces you that everything is very simple. Is that okay? I hope this is already give you the least square estimate. Is that okay? Now, if there's no question, I go back to the slides. Okay. And as I promised, we will give you a model, a probability model that would justify why we learn least square, right? Because we never going to explain what we're doing, okay? In terms of probability model. So the first one, okay, we need actually 4 assumptions here, okay? And the assumption is the following, okay? So remember when you do ANOVA, what we assume is each xi, right, will follow a normal mu mean I, right? This is what we have, right? So ANOVA will say each group, right? Observation actually follow a bell, right? That is ANOVA. And each group will have, I group will have different mean, right? I. So what now we extend in this model we have here is the following, okay? Also remember this is the thing we have, right? This you can write in this way. Remember that's how we write in this one, right? This is how we write the ANOVA model, right? If you remember, and we say this is, right, a normal 0 sigma square, right? So this is the ANOVA model. So actually it will be something similar, okay? What we assume now instead is we call, actually this is the mu I, right? This, what we want to explain, right, is coming from 2 parts, right? One part, this is determined by a group, right? And this is group information, right? Group structure. And the same here, right? This part is inside a group. This group is given by X information there, right? Y is the income, right? XI is the education, right? Education, now you have a number there, okay? It is given from this B plus XI, right? Because now this give us the group information, right? And at the end we have this guy, okay? Playing the same role is a random error, okay? And do note that for now, to just derive the property, we don't need the epsilon, the error, as a bell curve, okay? We don't need the bell curve yet, okay? We will use the bell curve at the end, but at the moment, we don't need the bell curve for the regression to work, okay? But later, when we do analysis, we will impose the bell curve. But at the moment, we don't need to put the epsilon as the bell, okay? And of course, this will inherit the same idea. Even though it's not bell, we still have mean 0, same variance. So this is same as what you learned from the ANOVA, right? The error term have the mean 0 and variance are same, right? And the next part, I think this is also the same, right? We have the same thing in the ANOVA is each one is independent, right? This is the same, also follow from ANOVA. Okay. And let me point out 3 and 4 why these two are important assumption and why we need to single these two out. Okay. Let me mention the very last one first because it's easier to describe. Okay. This means the random term you observe, or actually from data, over different observation are uncorrelated. Okay. And the first thing you can think, what is the epsilon in our model? Okay. In general setup, epsilon is the thing that actually was capturing is the thing that is actually not, you're not in the model, not in data. Okay. Suppose you want to explain income by education, right? So Y is the income and X education, right? And what is not in the education that explain income is epsilon, right? Maybe your parents' network, your IQ, your EQ, your AQ, your luck, many things, right? And what we say, this thing is not captured in your model, they should not be correlated across observations. And this assumption usually works, but when it doesn't work. For example, your data looking at is time series data. Look at the stock market, right? You can imagine if the price, okay, and price of today is likely to be related to price of yesterday, right? Suppose the price go up today, you expect the price would continue to go up tomorrow, right? In that case, these errors or the things you didn't model actually are related to each other over days, right? In these cases, regression is not doesn't fit very well. And probably ask, what can we do? Yeah, indeed, you need to go give a model to model those. And actually, this is a big class you can learn for a whole semester or even 2 semesters. It's called time series analysis. Okay, and which I think you will cover in 2021 for several chapters, but it's not our concern. Okay, but you can, if you want, this is something you want to study, right? So people study macroeconomics model, right? Unemployment under recession, right, is going to continue, right? There's some trend there. When there's some time trend, it will violate. And the other thing that it may easily violate is this guy. Okay, this variance the same. Actually, the same apply to ANOVA as well. And we assume variance the same across group. And this usually tend to violate when your data is what we call the panel data analysis. Okay. For example, if your data comes from Hong Kong, and probably do notice that people in Hong Kong Island is different from people in New Territories and people in Kowloon Peninsula, because of historical reason or because of the urban environment and so on and so forth, right? So you expect different location will have different variance, right? Because remember what's ipsilon sigma here? Sigma is the variation of the terms that you didn't measure, right? And probably people live in Hong Kong Island will be different from people from Kowloon Peninsula and New Territories, right? Or in the case of studying a data across country, right? Each country will have own different things, right? Some society are more uniform than others, right? In that case, that would have to be like this, right? Or look at the consumer data, right? Maybe boys and girls have different variance, right? And probably you know, right? Even look at the IQ, right? Variance of boy actually is much higher than woman, right? Men is much more higher variance than women. So assuming equal variance for all, it's going to be something that you can start. You can go to another course to study. Okay, so we focus on these simple model. Okay, and third one we want to look at is focus on X is actually random. Okay, this is the model that you can usually is not a problem when you talk about X is something we can change directly, like advertising expense and sales, right? As a company, you can change the advertising expenses to your own control, right? And then you make your everything will be fine, okay? But when you try to apply it to the case where XI is not your control, then in that case, that will be some issue there. And there will be some problem, but that would be an topic that you would have to worry when you go to grad school, okay? For undergrad, usually you don't need to worry, okay, graduate school. And then you need to learn many techniques to handle this problem, but I'm not going to talk about those. You need some instrumental variable or a lot of ways to make sure that it's random. Now you have to how to handle those. So we just consider case xi is the, we can easily control it. Okay, it's not random. Okay, is that okay? And these are the 4 assumptions here. Okay, with these 4 assumptions, okay, I hope you understand what the 4 assumptions here, and we're not going to do the proof. Okay, and these 4 assumptions actually lead us to a very nice result. Okay, is our A and B are actually the unbiased estimator of alpha and beta. Okay, probably you don't realize what this statement is. Okay, let me actually draw a picture to convince you this is a very important result. So look at the data. Okay, look at this scatter plot. Okay, x and y. Okay, and remember our assumption was the following. We said y is equal to alpha plus beta x plus epsilon. Okay, I'm putting I there. Okay, so this is telling us that for each x, okay, it is generated by some number alpha and beta. Okay, this is the number we don't know. Okay, but this number is a fixed number. Okay, and this is how it generates, right? So this line, okay, is what we have. This line is yi equal to, or just y equal to alpha plus beta x. Okay, and what actually in practice, what you observe, will have some random component there, which you don't know this guy. Okay, but what you observe is you will have some, you observe some number here. Okay, for this x, right? You maybe observe this number, you may observe this, okay? But on average, they are on this, on the mean of the realization is here, right? The mean is here, right? So you have another x1 here, x2 may here. These are the point that may end up, right? Depends on what you have, okay? The assumption 3 said they're the same variance, okay? So you look this thing, the same thing, okay? If you assume a normal, okay? If you assume a bell curve, that's something like this, right? We realize, okay, this is the bell curve. Or possible y, right? All the y will center on this one, center on here, this is the bell curve, okay? If you assume bell curve, need not be bell curve, but let's make it simple, make it assume a bell curve, right? So it's just saying that assumption 3 said the same variance, okay? So that is the data generating process, okay? So remember, you only get some of the data, right? So what does that mean? It means that you may end up in your data collection, you may end up in this point, end up in this point, end up in this point, and this point, this point, this point, maybe this point, depends on what data you draw, all right? You can end up like this guy, okay? And remember, you only observe the green one, okay? You don't observe the whole picture. So that means that when you try to fit a line, you may fit up here, okay? This may be your feeder line, right? And this feeder line is according to least square estimate, right? So you may end up in, this is your estimate A, okay? This is your estimate slope B, okay? So what Gauss Markov theorem said is, you can collect many data many times. You have many A, right? Average of those A is actually alpha. Average of this B is actually beta, okay? So if you've done many regression, and you will actually discover average of those is actually alpha and beta, okay? So that is the first statement means. Gauss Markov theorem saying that you use least square estimate, which we propose, minimize the vertical distance, is indeed good because If you do many, many times, these are the unbiased estimator of alpha and beta. Okay, this is the first thing. This is what we said, unbiasedness. Right, unbiased. And the second property you would want to say, okay, since they're unbiased, are they efficient? Right, because that is the point estimate, right? They efficient. Gauss Markov theorem said yes, this is efficient. Okay, when you consider other estimator is also linear in Y. Okay, and that's what is said here. Okay, it's efficient, and among the other that also linear in Y. Okay, that is what Gauss Markov theorem said. Okay, and recent advance in mathematics and statistics so that actually we can drop this idea. So that is efficient for whatever other estimator you want to do it. Okay, so that means that this least square estimator, okay, is actually the best possible thing you can imagine. Okay, because the reason said actually you can forget the linear. Actually, it's blue. It's actually BUE. Okay, but we follow the classical textbook. We just focus on this guy. Okay, we just talk about blue is best linear unbiased estimator. Best means in terms of minimum variance, right? If you remember, the graph is the following, right? So you want to hit this target, right? The best linear unbiased estimator means the unbiased, which means that in general it hits somewhere here, here, and here, and it is closest to the center. Okay, and that is the efficiency, right? The variance is smallest. Okay, so that means that least square estimate, least square regression or least square method that we have just done has a nice property. If you are willing to make that for assumption in our model, which is naturally progressed from ANOVA, right? ANOVA assumption will extend it to continuous numerical variable. That is the natural extension. Okay, so under this assumption, we have what we call the least square estimate is the best one. Okay, this is the best estimator you can have. Is that clear? Is that okay? If that's okay, we can go to interpretation. Okay. Now we have a model. Now we have a line there. Okay. This is a line, right? Because this is what it means. It just we have a model here, right? Now what we have is the following, right? So maybe I just try whiteboard, right? So what we have now is we start with a bunch of data, x and y, x, y. We have a bunch of data. This is our starting point, okay? And now we actually, what we do is we do a least square estimate, right? Compare, look at the distance that minimize it, right? And this distance minimizer, right? It's also a good thing. It's an unbiased estimator, right? So what we end up with this thing, we end up with a model, right? So we just forget about the data, right? We come up with a model, right? That simply what we have left is y hat is a plus bx, right? We forget about data, okay? So this is a, and the slope is b, right? Now we have this data here, a, no more data. We have a line with this model, okay? And this model now is the thing that we use to do our analysis, right? So we have the data, actually the information of data is condensed into this model, right? I mean, condensed into this model, right? So no more data with this model. This model represents our understanding of this data, right? From the data, we condense, right? We filter out, this is the information we have, okay? Now we understand how X and Y are related through this linear line, okay? So what does that mean? What we know is two things, A and B, right? So what A and B tell us? A will be telling us if X is 0, what's A, right? So in our leading example, which is the income, right? Y is income, X is education, okay? What is this guy? What is this? What is? This will be, if you imagine, this will be income of raw labor, right? Or what we call income of unskilled, right? Or income of uneducated, right? So if you do not go to school for any number of years, right? Or income of the kindergarten kid, right? Which never supposed to go to school, right? This will be income. If you stay in kindergarten, you never go to kindergarten, right? That's your income, okay? That would be, I mean, maybe a child labor. This is the wage you may charge, right? But this interpretation will be meaningful only, okay, if actually your data actually has some data nearby 0, right? Because actually what you do is, if your data, actually what you get the data is like this, right? Bunch of data here, right? And you basically extrapolate, go back to here, okay? Is it meaningful? I don't know. Maybe this is not very meaningful because there are no child labor in our society, right? So this is basically just an intercept there, just to fit the line, and no meaning. It's only meaningful if actually you have some data here, okay? Then going back could be a meaningful thing. If not, it's not meaningful, okay? But it just means 0 what you have, right? And second, what is the meaning of the slope? B, right? For B, it would just actually mean, right? If you increase education by 1 year, right? How much income you expect to increase, right? You increase by B, right? So that's the meaning of slope, right? You increase X by 1, that means Y increase by B, okay? This is expected increase, okay? Because this is, we forget about the other factor, right? The epsilon i's, right? So that is what we are trying to say, okay? And you should notice that this model, the usefulness of this model is you are comparing this model to a baseline model. You always have this model in your head because you are using X to explain Y. The baseline model is always Y bar, right? Because if I don't tell you anything about X, what would be your prediction is Y bar, okay? So what you're trying to explain or your model provide is something that is different from this, okay? So what you explain is actually this minus this, okay? And this is something that the model gives you, right? And how you explain it by X minus X bar, right? You are using the difference, right? Because remember your regression line will pass through the center of data, right? Say, pass through center of data, right? So what actually you are saying is you use this, you are using, what color should I use? Blue. You are using this distance, right? To explain this distance, right? Because you go from here to here, okay? And then the line tells you have to go up a little bit, right? So you're talking about saying that you give me X, I look at how it's different from the mean X bar, and I go up by B, right? So that is what the regression tells you, okay? In short, it means that I use the variation of X to explain the variation of Y, okay? So that is referred to the third bullet point in the slide, right? I hope that become clear now. Is there any question before we proceed? Okay, because this is just this guy. Okay, I just use the variation of Y, explain what X. Okay, so the key part here is it just shows the association. It's not saying that X cause Y, which is much more complicated, right? We are not saying that our income, okay, is automatically affected by education, okay? We're just saying that if education go up by 1, income go up by B. But is it a causal? I don't know, right? Because the fact that, for example, in this scenario, actually what might be driving the two is your IQ, your AQ, your EQ, and so on and so forth, right? Is people with a high IQ or AQ or EQ actually would study more and earn more. So showing they are correlated, okay, associated, explain each other doesn't mean that cause and effect, okay? To establish causality will require more than regression, right? Because you can regret Y of X, X of Y, right? There's no restriction to tell you which cause what. And to establish causality require us to know more than just running regression. For example, you do a control experiment, you change X, right? And Y will change, then that is a causal one, right? That can be done. But in education and income, you can show causal relationship if you give a bunch of kids, okay? You make those kids go to school more than the other, then you can do it, okay? But in reality, you cannot do it because of some ethical reason, okay? In those cases, you have to rely on something more than regression, okay? Or you need more further evidence to show you. And here we just show they are related, okay? I hope that's made clear. Running the regression alone cannot tell you education costs higher income. It just simply means that you saw a data, a guy has more income, you expect have more education, or you expect a guy have more education, actually have more income, okay? It doesn't tell you how they are related internally, okay? And if you want to show this relationship, actually you need more method. You will learn it if you go more advanced classes, but this is not our concern for this class. Is that okay? Is that clear? Okay. But of course, this is the first step to establish causality. If you want to establish causality, we need more evidence. Okay. Is that okay? Now, what remains is to show you the last thing of this model. Okay. Is in this model, we have estimated two things. We have alpha and beta estimated by A and B. Okay. And one thing we actually didn't talk about is this sigma square. Okay. And this sigma square is very useful, right? Remember how we do ANOVA is looking at different way to measure sigma square, right? And this does give us the F test. Okay. Similarly, in regression, this will play a very important role because the fact is now we estimate this alpha and beta, right? Because remember in ANOVA, we try to see if mu I is equal to mu J, right? Different group, right? We actually do the same thing. We want to see, right? If alpha is 0 or beta is 0. This will be something we will do in the next class, okay? But before we do that, we need to come up with an estimate of sigma square, right? Because remember in the ANOVA, this is estimated by say MST, MSW, right? And total within MSB, right? So this is the free way to estimate this guy, and then we do an F test, right? So we will have the same idea here, but now we come up with a way to estimate sigma first, okay? How to estimate this sigma, okay? It's not that difficult, okay? So we just follow the way we did, okay? What is epsilon? Epsilon is just basically the difference between the line and what you realize, right? So remember this graph here, right? So if you go back to the original model, right? So this is epsilon, right? I, right? So how you measure this epsilon I, right, is to actually measure the something like the sample, right? You measure your called residual is actually measured from your data over your fitted line, okay? So what does that mean here is, right, you fit the line, right? This is the line you fit, right? So this part is called E, right? This is E1, this is E2, right? This is E3, okay? And E4 and E5, so on and so forth, right? So basically, this is something you don't know, you want to know it, but how do you measure this guy? You estimate by looking at, you put in your data here, okay? You take a difference, okay? And I'll illustrate immediately in the next slide how you estimate it, okay? So for example, how you estimate like the following, okay? Remember, this is the model, the data we have, right? And I think A is 3 point, let me check. A is what? Look at the Excel, we have A is 3.9, B is 0.7, right? A is 3.9, okay? B is 0.7, okay? So how you get this y hat, right? It's just 3.9 plus 0.7 times 1, right? Because this is what it means, right? Let's look at this guy, right? Put 1 here, right? Because that is just A plus BXI, right? This is y hat, right? And how you get this number here, EI, right? Will be just YI minus YI hat, right? So it's 4 minus 4.6, right? So basically just the first column minus the second column give you 0.6, right? So you would do the same for the rest, okay? And okay, that's how you do the EI, okay? Lastly, I want to say one more thing is you can estimate sigma, okay, by this formula. You square them and over n minus 2, okay? And why this is the estimate of sigma square? Because you should be doing this, right? E bar, right? Minus 2. The reason that you don't need to subtract this is because this is 0 always. Okay? We don't prove it, but this is always 0. The average of this E1 up to En is always 0. Okay. This is by construction. Okay. This is called E bar, right? And the last thing is, because of time, so y minus 2 here, the reason is very simple. Because you estimate A and B, you estimate 2 parameter, so you minus 2. Okay. Same as the one you learn in your sample variance, right? You estimate 1 x bar, then you subtract 1. Now you estimate 2 things, you subtract 2. Okay. So that is the reason. And I guess that's all today. We'll continue our journey on Wednesday. Hopefully we finish them all. Okay. It's not very hard. Okay. Okay, I'll see you on Wednesday. No, we don't.